Okay, part of our lesson today is to make sense of the Argan diagram, and in order to do that we need to kind of compare and contrast it with the Cartesian plane. Y'all have been working with the Cartesian plane for a super long time. In the Cartesian plane, this axis right here is called the x-axis, and this axis right here is called the y-axis. And you can graph lots of points when you're on here, and you'd call those points x and x comma y, right? Where you just come up with some x value here, some y value here, and that would be the x comma y. The Argan diagram is slightly different in that this axis is the real number line, so just all of the regular standard numbers, while the y-axis, or what is normally the y-axis, this vertical axis right here, these are the imaginary numbers. So on this axis, instead of plotting an xy coordinate, what we would plot is a complex number like a plus bi. In this case, you would go some a, in this example I've gone in the negative direction, in the real direction, and some b value in the positive imaginary direction. And so this vector, in fact, right here, that ends at this point, but it is considered a vector from the origin, is a complex number. So you could have some other complex number. Let's say I had 3 plus negative 4i. Well, in order to graph that, you would go over 3 and then down 4. And your vector would end up looking kind of like that, where you go 1, 2, 3, 1, 2, 3, 4. And then this, including the I, sorry, I didn't mean to cut the I off there, including the I, that would be that vector right there. So very, very similar looking. And yes, in fact, as was asked in one of the classes, you could put these two together. And in fact, the video that I showed you actually does that with this fabulous visualization. If you watch this video, it's linked in the week 1 materials of when there are imaginary zeros in for like a parabola. This is kind of how you could picture it. So the flat paper here is like the Cartesian plane, and the Argan diagram is like this translucent grid that's kind of coming out of the paper, and presumably also below the table. So we brought that in class, totally nose on. Okay, other important things that we're going to run into with Argan diagrams is that they kind of overlap with something called polar coordinates, which I'm going to get to in a little bit. But the things that you're going to care about here are the modulus and the argument. And these are just fancy words for other things you are already super familiar with. The modulus is the length of the vector, and the argument is the angle from the real axis. So in this example that I have here, where I have 3 plus negative 4i, so this is our vector here, I just want to know the length of the vector. In order to do that, y'all are just going to have to remember a little bit about Pythagoras, or what you think you know of Pythagoras. Here's a right angle. This is 3. This is 4. If you follow your nose, you're going to get that C is 5. I'm hoping that it's okay if I kind of skip the steps here. But this is 5. So in this case, the modulus is 5 units long. And that's just saying, like, how far away is the end of my vector from the origin. And then the argument is going to be the angle from the real axis. To do this, you're going to have to remember ye old SOHCAHTOA, or however you want to say it. And because we now have 3 different side lengths, we can definitely deal with this. I'm looking for this angle right here. And we're going to have to remember a little bit that we're sitting below the axis, so that will factor in here. And now with 3 different sides, it doesn't really matter what we pick. I'm going to just go opposite and hypotenuse, so that would get me the sine. So I can say that the sine of my angle is going to be equal to 4/5. And so that theta is going to be equal to the inverse sine of 4/5. Plug that into a calculator, and you will kick out about 927/10,000ths, which is a little bit less than 1 radian. And because, again, remember that we're below the axis, normally you would go the counterclockwise direction if you were doing this. So since we're below the axis, this is actually going to be a negative 0.927. This is our argument. I made a separate video quickly on radians as a reminder, but in case you need that. So modulus is 5, argument is negative 9.27. And hopefully that makes sense. If I say anywhere on here, if my modulus is, in fact, let's draw this out. Let's say I said my modulus was 3 and my argument was 2 pi over 3. What I might start with is the argument and say, okay, this is 0, and then 2 pi over 3 is going to be kind of if we split this half, the top half, into 3 equal pieces. So this right here would be the angle. Sorry, oh, that was terrible. Let's draw that again. This right here would be the angle, 2 pi over 3 radians. And then I just want the modulus of 3 units. So let's say that's 1 unit, that's 2 units, that's 3 units. Then my vector, or my complex value, would be right here. So that's one way of describing it. A different way of describing it, of course, is going to be if you use the A plus BI. So one of the questions I might ask you is, okay, now that we're over here, what is A plus BI? So really now what we need to do is kind of go backwards. So again, I'm going to give myself this lovely right triangle that I'm going to be working with here. I know that this yellow part is 3 units long, and I know that this angle right here, if this part is 2 pi over 3, that this is going to be pi over 3. So what I'm going to want is I'm going to want my real value, A, I'm going to want my imaginary value, B, and I can do that with just a couple bits of trig. So to get my A value, I might say that the cosine of pi over 3 is equal to A over 3, and you can solve that for A, and you will get approximately, oh, just kidding, exactly 1.5. And then if you were looking for your B value here, you could do the sine of pi over 3 is equal to B over 3, and you would get that B is equal to about 2.6. Cool. So then what we really have here is our real value is 1.5. Our imaginary value is about 2.6. So the coordinate that we would get, or the complex number, is 1.5 plus 2.6i. This also describes that yellow vector. So we can go forwards, we can go backwards. That's the gist of it. And of course, as many of you are probably screaming, you caught that I didn't go back to check, and since we're in quadrant 2, it's a negative 1.5, so make that a negative 1.5. Obviously, when you're solving and it's just a distance on the triangle, it is still positive, but we need that negative. Okay, so now let's talk polar coordinates. Okay, so now let's get into polar coordinates. I now have a 1 unit long modulus, and my argument is pi over 3 radians. And what I'm going to do is I'm going to explore how I can use this to get me to what polar coordinates are. And this always, as with all of the other things, comes back to trig. So let's say I am looking for my value of A. I have enough information at this point to use it. So what I can do to find my value of A, again, is I can say, since A is the adjacent side to this angle right here, I could say, cool, the cosine of pi over 3 is equal to my length A over the hypotenuse, which in this case is 1. But hopefully, all of us are okay with the fact that A divided by 1 is just A. So I'm going to actually simplify this and write this out as just A. And then for the very same reason, if I'm looking for B here, that because it's my opposite side here, that I can write this as the sine of pi over 3 is equal to b over 1. But again, I don't really need the over 1 because that's just b. Well, notice here, what we have is that a is equal to the cosine of pi over 3, and b is equal to the sine of pi over 3. Now imagine if this was 2 units long, instead of being 1 unit long. What would have happened here? Well, instead of being over 1 here, it would have been over 2. And the way that you would resolve that is you would just end up multiplying both sides by 2. So really what we have here is that we have another way of describing these coordinates. And so what a polar coordinate looks like is it is normally written as z is equal to r times cosine of theta plus I sine of theta. And if you were in the class where we talked about cis, this is just an abbreviation for this because it is cosine and I sine of something. The r sitting out front deals with the fact that if this is not 1 unit long, you just have to multiply by the scalar that would make it however many units long you want. Okay, finally in summary. This point right here is what we're caring about. You have known it for many, many years as the point 3,4, and it absolutely is, and it will remain to be that way. However, we could also describe that as a complex number where we wrote that as 3 plus 4i. So we've got our Cartesian coordinate of 3, 4. We've got a complex number of 3 plus 4i. That's what we call an Argan diagram description. And then if you happen to have the modulus, which in this case is 5 units, and if you have the argument, which in this case is 0.927 radians, then you can come up with the polar coordinate version. In this case would be z is equal to 5 cosine 0.927 plus I sine 0.927. But if you know anything about mathematicians, you will know that this is way too long for us to write out. So sometimes we abbreviate that by saying z is equal to 5 cis 0.927. And the cis, again, is CIS. So this is our polar coordinate. Okay, so Cartesian, complex numbers of the Argan diagram, or when we get to polar coordinates. Let me know what questions you have. I know this was kind of long. Hopefully I'm trying to make up for any confusion that happened in class today. And we'll go from there.